Thank you everyone for coming to my talk. My name is Jeremy Wagner, and I'm a technical writer at Google for Chrome, focusing on web performance and core web vitals. I'm stoked to be a part of JSConf Japan to give this talk about a new responsiveness metric we've been working on at Google called Interaction to Next Paint, or INP for short. I apologize I couldn't be here to present on the live stream, but there is a holiday in the United States, and that has prevented me from showing up in person, well, virtually, anyway. So let's get rolling. Before we can get into INP, we need to clarify responsiveness. And when we talk about responsiveness, we're talking about how quickly a user interface responds to user input. You've almost certainly experienced poor responsiveness. It occurs when you interact with something on the page, but the visual feedback of that interaction is significantly delayed. Poor responsiveness makes a page seem unreliable. This unreliability means you may tap multiple times on a page element, causing multiple unintended inputs, or worse, no response at all. We want good responsiveness because it gives a sense that the page is reliable. So what causes poor responsiveness? To answer that, we need to talk about tasks. In order for a web page to provide a user experience, a web browser must orchestrate a lot of work. To do that, it uses threads. The most important of these is the main thread, and it's where most work occurs, including the work your JavaScript code queues up. Now, you don't want your main thread to look like this, stuffed to the brim with tasks that are always running, constantly blocking user input, and making your pages slow and unable to respond quickly. But back to the topic of tasks. A task is a discrete piece of activity that the browser runs. Again, usually on the main thread. And in this specific case, we see that activity consists of script evaluation and compilation. Each task, trite as it sounds, takes the amount of time that it requires to complete. However, if a task requires too much time, it affects how quickly the main thread can respond to subsequent tasks. And when that happens, that task becomes a long task. A long task is any task exceeding 50 milliseconds. The portion of the task longer than 50 milliseconds is known as the task's blocking time, which is the amount of time the main thread is unable to respond quickly enough to new tasks. This is a significant source of poor input responsiveness. Long tasks can cause pages to be sluggish and unable to respond quickly to user inputs. But it's vital to remember that tasks drive everything that happens on the main thread, and that includes interactions. Here you can see a single task that shows a loading spinner as a result of a key down event. These types of interactions, and far more, make up the user experiences we use every day. And those interactions need to be fast, because what we want is visual feedback sooner. And that visual feedback comes in the form of a new frame that the browser paints. Hence the name of the metric, Interaction to Next Paint. One way of optimizing work in the browser is to avoid long tasks. Too many long tasks are a user experience problem. But more than that, it can also be the accumulation of many small tasks that can be problematic as well. In either case, the important thing to remember is that there is also the time that the renderer requires in order to present the next frame. This involves some tasks that run on the main thread, such as style and layout calculations, but there's also time involved on the GPU and compositor threads to get the next frame ready to paint. Long tasks are easier to identify in profilers, so they're a great place to start optimizing. Now you might be thinking, why are we spending so much time talking about tasks? And the reason for this is the event loop, which is something I won't get into deep detail over, but it's important to know just a bit about it and how long tasks, or many small tasks, can sabotage the user experience. The event loop is a continuously looping task queuing mechanism run by the main thread. It loops around, and around, and around, and around. And if this is the mental model you have in your head when it comes to the event loop and tasks, you're pretty much spot on. Well, minus the mayhem and potential for serious injury, I suppose. Anyway, the event loop keeps doing its thing until a task is queued up. And when that happens, the event loop will pick up the task, a key up event handler, for example. And when the event loop has picked up the task, it processes it and pops it off the queue when finished. Then if the task caused any changes to the layout, the browser has to do rendering work to reflect those changes before the next pane. When that rendering work is completed, the browser presents a new frame, which is the visual feedback from the task. And if tasks don't become long tasks, or if there aren't a lot of small tasks that pile up in the queue, everything goes smoothly. But when there is too much work, visual feedback is delayed. That stuttering, janky feeling you get when things aren't going smoothly, and even outright freezing of the browser tab in extreme cases. IMP is a metric that quantifies a page's ability to avoid doing these things. This will be a quick rundown of how IMP works, but for the full story, you're going to want to read the official documentation at web.dev/IMP to get a sense of all the little nooks and crannies in terms of how it works, because it is a complex metric, but I will do my best to summarize. IMP is a metric that observes certain interactions using the event timing API. This API receives an entry every time the user interacts with the page, and contains timings for those interactions. Unlike first input delay, IMP measures more than just the input delay of the first interaction. If you don't know what an input delay is, don't worry, we'll get there. And finally, it chooses the single worst interaction, or close to it, which is intended to represent the page's overall interaction latency. It's a bit more complicated than this, so more on this in a bit. The takeaway from all of this is that IMP is all about the time it takes for a new frame to be presented for the current interaction. From the time the operating system recognizes an input, for the browser to pick up that input, for the event handlers that drive it to run, and finally, for the time it takes the browser to do all the rendering work to show you the results of that work. However, IMP doesn't measure all interaction types, but it does measure those that drive most user interactions. And those include keyboard interactions, clicking on a mouse or another fine pointer device, and taps on touchscreens, such as on a phone or a tablet. It's also important to call out what doesn't get taken into account for IMP, at least directly. This isn't an exhaustive list, but just a few things that are important to call out. Hovering over elements with a fine pointer device, such as a mouse, don't count towards IMP. However, that could trigger animation work that may affect a soon-to-be future interaction. For example, say you have a button that has a hover animation. If that work is occurring as the user clicks on that button, that could delay the presentation of the next frame for that interaction. Network activity isn't factored into the duration of an event for IMP. However, fetch requests, for example, are asynchronous and can have an indirect effect on future interactions. Scrolling isn't taken into account either. However, users can scroll at the spacebar, or page down or page up or arrow keys. So if an event captures any inputs for those keys, that could theoretically queue up tasks that may affect that interaction, but the scrolling itself isn't considered. All qualifying interactions are recorded throughout the life cycle of the page. When the page is unloaded for a new one, the page's IMP is calculated by choosing one of those interactions. Now, for pages with relatively few interactions, 50 or less to be specific, such as pages with mostly text and images or just simpler applications with fewer input requirements, this is often the interaction with the most latency, or the worst interaction. However, some pages may have many interactions before they're unloaded, such as single-page applications and rich apps like in-browser games, text editors, and other application types with with complex requirements. In such cases, we don't want to penalize developers by selecting what could be an extreme outlier of interaction latency. In cases like these, the 98th percentile of interaction latency is selected. The resulting value is the page's IMP. The idea is that by selecting the worst interaction on the page, or closest to the worst, you have a value that represents a page's overall interaction latency. Think of it this way. If your IMP is in the good range, that is 200 milliseconds or less, all interactions on your page are reliably fast. If your IMP needs improvement or is poor, then it's likely that some or even most of your page's interactions are too slow. But what does an interaction look like? The first part of the interaction starts with user input from one of the interaction types we just discussed. For example, say a user clicks on a button to open a menu. When the user clicks, there is a period of time between when the user clicks and event handlers begin to run called the input delay. This is what first input delay measures, but only for the first interaction. IMP measures more than this. It measures the entire interaction, which you'll see shortly. Now, you'll always incur some input delay because at the very least it takes time for the browser to receive the input event from the operating system. But that delay can be increased due to tasks on the main thread as the input occurs, long tasks in particular. If you have a lot of long tasks on the main thread, input delays can increase. Once the input delay is over, the event handlers responsible for driving the interaction can run. Here we see a set of event handlers for a mouse click. The goal here is to ensure those event handlers run as fast as possible. You don't want these event handlers to run for too long because the browser has to do work in order to present the visual feedback the user needs in order to see that something has happened as a result of the interaction they just made with the page. Once the event handlers finish running, the browser then needs to do rendering, painting, and compositing work in order to present the next frame. This is called the presentation delay, and all this work to present a new frame to the user needs to occur as quickly as possible as well. The presentation delay represents just the main thread portion of the rendering work. There are a lot of nooks and crannies in how long this takes. And it gets more complicated. A single interaction can contain multiple input delays, event handlers, and presentation delays. Here you can see a mouse interaction where a frame is presented after the user pushes down on a mouse button. But then when the button is released, a new batch of event handlers and rendering tasks must run to present additional visual feedback as a result of the user lifting their finger from the mouse button. In cases where there are multiple events in an interaction, the longest duration of the interaction will be chosen as the latency for the entire interaction. Now we're ready to talk about how to optimize for IMP. And when you're optimizing for IMP, you're going to want to first measure it, and not just in lab tools, but using field data. Field data is important because it lets you know how your website is being experienced by actual users. And one way to gather that field data yourself is to use the Web Vitals JS library. The library exposes methods for each of the core Web Vitals, but also INP. Each method takes a function that exposes properties for the observed metric, most importantly the metric name, INP in this case, its value, as well as the element responsible for the interaction, which is provided as a selector string by a function in the linked gist. When you've got that field data, and you know which elements are responsible for high interaction latency, it's time to go into the lab and start testing those interactions, because it's lab tools that will give you a bit more insight into why interactions are slow. One useful tool is in Chrome DevTools starting in Chrome 106. We can now rely on the Performance Profiler to show interaction details right in a performance trace. So say you know what element is causing trouble. You can test that in the Performance panel and dive right into that interaction. For example, you can see in the interactions area near the top of the trace, there's an item labeled Interaction Type Click. This means that the interaction counts towards INP. And we can see how we have a long task in our hands that has two events for mouse down and click, with the click event handler taking the longest amount of time. This method lets you dive right into what's causing the delay during processing and give you some ideas for how to break up or optimize that work. Because this particular long task causes quite a bit of delay in the next frame being presented. But if you want something a bit more focused, you can also see interactions in the new Performance Profiler in the Performance Insights tab in Chrome DevTools. It's a streamlined version of the Performance Profiler we're all familiar with, but a little bit easier to use. So you've profiled an interaction, and now you want to know what you can do to optimize it. So what do you do next? The answer to this is rather complicated, and it depends on your website. Every slow interaction has its own fix, but I'm hoping the following provides you with a sort of general framework for getting your tasks under control. The guidance in this part of the talk is largely based on an article I wrote for web.dev, so if you want to get the written version of this, head on over to web.dev/optimize-long-tasks. One good piece of advice developers tend to follow is to split up work into separate functions. We do this for a number of reasons, such as maintainability, readability, and easier testing. It's easier to follow, and we get to isolate work into separate little functiony units. However, where JavaScript is concerned, because all of the work item functions are executing in the same function, it will group all of that work into a single long-running task. Now that's not great from a performance standpoint, because instead of 5 little functions doing their own thing and their own tasks, you just have this big old task that will block the main thread from doing new work, including work that occurs because of user interactions. This will affect your INP if users are trying to interact with your website. You need to break this work up. One way to do this is to yield to the main thread, which breaks up tasks. Take this homemade yield function. It uses a promise that resolves with a call to set timeout. And this works because set timeout will schedule its callback in a new task. And with that yield function, you can then yield to the main thread after every little discrete piece of work by awaiting the custom yield function. Now, note that you don't have to yield after every function. For example, if you have critical work that updates the UI, you can yield after those functions to give the renderer a chance to do that work. The result is that now you don't have one giant task that has to run every little function, but a task for each separate function. This gives the main thread more opportunities to yield to other things like interactions or background work that the user doesn't necessarily see or care about. Now, is this approach a bit hacky? Maybe, but there could be a better solution in the future. One proposed part of something called the scheduler API is scheduler.yield, which will work much the same way as the promise-based solution I've shown you, but it will allow developers to tell the browser directly if the current task should be broken up and yield to the main thread at specific points. I'm excited for this potential addition to the web platform, as it will give developers a way to break up work without user-land hacks. But I should take this time to remind you of one very important thing. Breaking up work still isn't enough on its own. Remember, INP is all about time it takes to present the next frame. If you have a ton of little tasks that are running all the time, or lots of huge tasks that are blocking the main thread, you can't present the next frame after a user interacts with a page as fast as you might need to. You still need to do as little work as possible. However, another way to prioritize user-facing work is to explicitly yield to user interactions with the isInputPending method. IsInputPending is available in navigator.scheduling.isInputPending, and it returns a Boolean if the user has interacted with an element on the page. In this code, you can see how the doWork function adds separate functions to an array of tasks. Then, within a while loop, this code checks if there is a pending user input. If so, we explicitly yield to the main thread so that the interaction can take place. Otherwise, we shift the next task off the front of the tasks array and run it. The effect of isInputPending, at least from the perspective of the new performance profiler, is evident. Here we have a large blocking task that doWork kicks off. However, in the middle of that task, isInputPending is used to see if a pending user interaction is waiting for the main thread, which is brought on by clicking a button to open a navigation menu. When isInputPending returns true, we yield to that interaction and allow the browser to handle it. But there is more that you can do, and that involves prioritizing tasks. When using this strategy, you should think of tasks in terms of what's critical and user-facing and what isn't visible or immediate. This figure shows how browser prioritization of tasks works by default. And when you leave things up to the browser, it will try to prioritize inputs based on a system of internal priorities. It works pretty well, but sometimes it needs a nudge. The post-task API, currently only supported in Chromium browsers and Firefox behind a flag, adds more flexibility to how browsers can schedule work. More importantly, it allows the developer to schedule work based on a system of 3 priorities. The first of which is user blocking, which is for critical work that must run at high priority. Think of this priority as best for interactions that need to be processed as soon as possible. Then there is user visible, which is for medium priority work that may result in visual changes to the user interface, but maybe isn't strictly critical. And the third is background, which is for low priority work, especially work that the user doesn't necessarily see or know is happening. Let's say you have a bunch of work that doesn't result in any changes to the user interface. This would be background work. The shape of the post-task API allows you to specify a priority value using one of the priorities I mentioned previously. In this case, all the tasks are set to run at background priority. Now let's say you run that work, and then the user interacts with the page to open a navigation menu, for example. The background work will run at lower priority, but if the user opens the navigation menu, those background tasks will yield to the interaction. This is an exciting new API, but even more exciting is that it's still developing. There are discussions currently taking place about adding finer-grained priorities as well as other mechanisms, such as the scheduler.yield functionality I mentioned earlier. On a final note, I feel it is very important to make clear that INP is a developing metric. The Chrome Speed Metrics team at Google is still fine-tuning this metric, so some of what I said in this talk may change, but the fundamentals should still hold true in the future. And with that, thank you for your time and thank you for hosting me. If you have any questions about INP, obviously I'm not available to answer those today, unfortunately. But you can always reach out to me on Twitter at Malchata, that's Malchata, or through the contact form on my website at jlwagner.net. I look forward to answering any questions that you may send me, and I will try to get back to you as soon as possible. Thank you again.